This video lesson is about finding segment length.
In our first example, we're asked to find the length AB. And keep in mind that when you see two capital letters like this, that we're not really just talking about the segment, but we're talking about the length of the segment, or you could also think of that as the distance between the points A and B. When we find the length of AB, we're going to be using the Pythagorean theorem when we employ the graph method. So if we take a look at our graph, because the segment AB is neither horizontal nor vertical, but a diagonal segment, we can't just count the distance either horizontally or vertically. But what we can do is make this into a right triangle. So let's go ahead and do that by connecting A to B or B to A with a horizontal and a vertical segment. And it doesn't matter if you do it right there, you could also connect it over here. We're only going to use one of these right triangles though. All right, so once you've connected point A and point B, we need to find the legs of this right triangle that we just drew. And I'm going to use some language now that you'll hear again when we do the algebraic method. So I'm going to call this the change in y. And I'm going to refer to the distance, the horizontal distance, as our change in x. And if you've never seen them used this way before, those delta symbols or arrows, that means the change in, and we'll use that a lot in geometry this year. So when I look at the change in y, I'm asking myself, how does y change from where point A is now to where B is down here? So if I look, the y-coordinate of point A is 4, and the y-coordinate of point B is 2. So that's a change in 2. Now the easier thing to do here is to just count that the segment is 2 units long. So if we find our change in x, we're going to do the same thing. And this time, let's just count over. So we're going to count over 1, 2, 3, 4, 5, 6 units. We could also say 4 minus -2 is positive 6. All right, so the change in x is 6 units. So now we have a triangle that basically has a short leg of 2, a long leg of 6, and we're trying to find the length of the hypotenuse. Let's pretend that is connected there. All right, you learned about the Pythagorean theorem in 8th grade, but we'll review, and we will use it so much in geometry. So remember, with the Pythagorean theorem, we say that anytime we're given a right triangle, that we can call the legs A and B, and the hypotenuse is C. So an equation, if I want to find the length of the hypotenuse, I can say that A squared plus B squared equals C squared. Okay, so let's go ahead and use those values that we identified in the triangle. So since we're trying to find the hypotenuse, we're going to use 2 and 6 for the values for A and B. So 2 squared plus 6 squared equals C squared. I'm just going to go ahead and use C still for this length. All right, so 2 squared, 2 times 2 is 4. 6 squared, 6 times 6 is 36. That's going to give us C squared. And now we add 4 and 36. So that's going to give us 40. Oops, that kind of looked like a 90. 40 is the value of C squared. Now, 40 is not our final answer. We have to take the square root of both sides. So if you remember from algebra, we'll have to take the square root of both sides to find the value of C. So the square root of 40 is the value of C. And now we can either change this into a decimal, or we could write this as a simplified radical. So the square root of 40 is the same as, I could break this down into 4 and 10. I know I can take the square root of 4 but not 10, so I could call this 2 root 10 is the value for C. All right, so I could say the length C is 2 root 10. Now, I seriously doubt anyone thinks in terms of radical expressions. So if you plug that into the calculator, or if you do the square root of 40 in the calculator, you should get approximately 6.325. So if we use the calculator, we want to include 3 numbers to the right of the decimal when we go ahead and round. So to answer our question, the length of AB is approximately 6.325, or 6 and 325 thousandths units. In example 3, we're finding a distance again. So similar to example 1, we're finding the distance EF, or we could also say FE. All right, so what I would recommend is when we start this problem, let's put these 2 points in a table. So I'm going to do a table of values, and I know you use a lot of tables in algebra. So for point E, and it honestly doesn't matter what order you put these in, E we said is -2, -5, and F is 3, -1. So remember when we're looking at an ordered pair, it goes X, then Y. So we're just putting these points in a table. The reason we're doing this is it's going to make it easy for us to look at the change in X and the change in Y. So what I would ask myself is from -2 to the number +3, is that an increase or a decrease, and by how much? So from -2 to +3, that's an increase, and that's an increase of 5. So I'm going to write out here +5. Then on the Y side, we'll do the same thing. So from -5 to -1, is that an increase or a decrease? Well, it's an increase because it's becoming less negative, and it's an increase of 4. So I'm going to write +4. So somewhere else, I'm going to write my change in X equals 5, or you can still write +5, and then my change in Y equals 4. So now what we could imagine here is if the points have a change in X and in Y, so in other words, if they don't have a common X coordinate or a common Y coordinate, they're not going to be horizontal or vertical distances from each other. They're going to form a diagonal segment. And we could think about that without graphing. If you wanted to, you could kind of sketch these points on a graph, but I really want you to understand the algebraic method of doing this as well. So what we might do next is we might just kind of draw our triangle. So I'm going to draw a right triangle, and it doesn't have to be to scale at all, but just like we talked about when we did this graphically, we're going to label our change in X. We're going to kind of think of this as an X-axis and a Y-axis. Our change in X is going to be down here, and that's going to be 5. And our change in Y will be over here, and that'll be 4. So now, just like we found the distance in the first example, we're going to use the Pythagorean theorem. We're solving for the hypotenuse, so we're going to use a squared plus b squared equals c squared. All right. And I'm going to kind of partition this off so it doesn't get too confusing. I'm going to do the work here, though, in black pen just so that it shows up. All right, so a squared plus b squared equals c squared. It doesn't matter which of these I identify as a and which I identify as b, as long as the hypotenuse is c. So 5 squared plus 4 squared is c squared. 5 squared we know is 25. 4 squared is 16. So that's going to give us c squared. So now when we add those together, 25 plus 16, well, 25 plus 10 is 35, plus 6 more is going to give us 41. And last but not least, we're going to take the square root of 41. And that's going to be our exact value of c. Now, we can't simplify the radical expression, the square root of 41, but if it bothers you or if you want an idea of how long that is, we could actually just take the square root of 41 in our calculator and we should get that it's approximately 6.403. So that's going to be our approximation for how long that segment is. So that is I would take either of these as acceptable answers to the distance between E and F. Congratulations, you made it to the end of the lesson.